Where's the stairs? I want the one that has a bunch on it because it's a good practice one. So we're looking for patterns. I'm going to give you a couple of minutes to look, just use the top one and write down anything that you can about patterns. What do you notice for a pattern? So just use the first one. This will be one of the harder ones that we do. The other ones aren't so bad, but I know you can find a pattern. Black. Okay. Not necessarily between figure 1 and 2. Nice try though. Just mess around on your paper. Evan, go up and write down on the first one what you wrote down in your book. How were you looking at this one? Evan is writing down on the Promethean board. So he wrote down 1, 3, 6, and 10. Wow, I never actually really thought about it that way. I think that's kind of what you were saying, isn't it? So then he wrote this. So this would be the first one, right? It's actually 2 different patterns that you're seeing here. And then for the second one, he was going like this. Would you put anything on the last one? Could you make a logical guess of what the last one would be? Where are you getting 2, 3, 4, and 5 from? What do you actually?
So the number of squares. Well, the number of squares.
The number of squares.
Figure 1 adds 2 to the figure 2.
So you're actually adding the next figure number to it then. Figure 2, you're adding the 2 here. Figure 3 is being added here. Interesting. I actually had never seen it that at all. I like that. That's good. But I'm off a little bit. It's not exactly matching up here because you don't really have 3 squares here. You don't really have 6 squares here. So a little fine tuning needs to be done. You got a great thing going on. One thing that I want to say that you could actually do this if you have a place on your scrap paper this one, on the side somewheres. There is a way to tell whether it's linear or whether it's quadratic. So this one right here, if I had this pattern right here, I could see that how it's changing is it's going up by 2. This is different than what I would see if it went like this. This would be different. This is going up by 3, and then this is going up by 9, and then this is going up by 15, and this one is going up by 21. Those are 2 different functions. Can you tell me about either one of them that you know for sure? Yes? So this one's linear because this is your rate of change. It's changing the same. It can't be linear unless the slope stays the same. So that means that we have y equals 2x. Is that it for that one? Is it just y equals 2x? What is it? So that's why having the 0 number is always good. If you have the 0 number and you have the rate of change, then you can write an equation of a line. Okay, that's what linear functions. You've been working on those forever. What you haven't been working on is quadratics. And so is it changing the same? No, but this is how you can tell that it's a quadratic. If you do, this is called a first difference. You're looking for the difference between the numbers. If you do a second difference, that's where you're going to know if it's quadratic. So to go from 3 to 9 is 6, 9 to 15 is 6, and 15 to 21 is 6. That's how you know it's a quadratic, because the second difference, you get the same number. So this is definitely a y equals x squared, but is that it? It is. It would actually be. There's your 0 number. That's still true for 0. It would be plus 0. but it doesn't work for all the numbers. If I substitute in 1, what's 1 squared? 1, what do I need to get? So, what's 2 squared? 4, and I need a 12. What's missing? Times 3. Now it would work for all of them. My point on this one, though, is to show you that the first difference is linear. The second difference is quadratic. The next function that we're going to be working on is that these are actually being multiplied. It's not a difference. Now you're going to be looking for multiplication between those, and that's a different function. So if you want to know if something's quadratic, look for the second difference, and you're going to know that it's definitely quadratic. I don't want to say too much more on this one. I mean, there are some great ways to figure this out. This one is actually a little bit difficult to be able to figure out. We're going to circle back around to this one. I want to give the other class a chance to try to figure out some patterns that they're seeing. So let's look at, there were 2 back here in linear functions that were quadratic. I didn't tell you back then that they were quadratic because I just wanted you to mess around with them, but I don't think hardly anybody did. And so if I look back in my notes, there's the regressions, and then we did a picture after regressions, and here we are right here on this one. We had this picture, and then we had another one. And nobody really did anything with these ones. I didn't really force the issue on it because I knew that we were going to be coming back to it. So look before we started quadratics, look for these pictures in your notebook. Go all the way back. Here's chapter 1.1 in quadratic, so it's right before chapter 1. From a picture. All right, so we're still trying to write an equation of this. I even struggle at this stuff. This is not something that I perfected now. Quadratics and linear functions and polynomials and rational functions, all of that, I have mastered the algorithms. I love it. But this is the part that I'm not so good at either, is being able to create equations from pictures. So it does take a different way to think about it. I mean, if you think about it, all my teachers and professors all taught the algorithms. I taught algorithms for 12 years, and now in the last 5 years, I switched to a little bit different way of thinking about mathematics. That's how they do it in certain places, and they're further ahead in mathematics than we are because they're not doing just algorithms. They're trying to logically think about mathematics. So looking at this, try this one now. Try to create a pattern. If you don't have this one, just get out a piece of paper and draw the rectangles. Just looking for a pattern. Looking for any pattern. We're going to follow through on this one. Looking for a pattern. Anything at all. These are area models. Start thinking about it as area. Good. I would erase. It's good. Just trying to think of something. And how do you find area? How do you find area? Don't have area as the final answer. Don't have area as a final answer. How do you find area? Exactly. So why don't you try looking at those numbers there? See, I never told you to look there before. Never told you to do that. So if these are area models, then maybe you want to start looking at, and then this is a 3 by 4. This is a 5 by 6. Are you starting to see any patterns there?
1, 3, 5.
Yes.
Up by 2. And up by 2. Yes.
Good job, Evan.
Up by 2 on both.
So I could try to write, they have a pattern. There's a definite pattern here. I could try to write an area model formula kind of thing. Like, what would n be? What would n represent here, or x? I'm going to use n. So, yes, like what in here would I want to represent n? I have to start with something. Like I would say at the very beginning where I'm looking, I would say that n is going to be a 1 square. That could be my n. And then I'm multiplying by what then? If I'm defining n, I define n as being a 1. what would be, what would I be multiplying here then? I could say maybe, again, I'm still working on this stuff too. I have a really good idea of how it works, but I still have to like work through the process myself. So if n is 1, then what would 2 of these right here be? What do you think that 2 of them would be then? Okay, so if I say 2n, you actually have to check your equation now. This is figure 1, so we'll say figure 1, figure 2, figure 3. So figure 1, if I substitute in a 1, I get 1 times 2 times 1. So 1 times 2 is 2. Fine, it works for that one, but is it going to work for the next one? The goal is to get it to work for all of them. So for this one, I'm still using n and times 2n if I think that's the equation. So what would n be on this one? N on this one would be, we used 1 because it was figure 1, not because of the 1 here. We used figure 1 for n. What are you using for the n on this one? 2. You can't use 3 because 3 and 4, you have to use the figure number. So if I do 2 times 2 times 2 is 4, do I get 8? No, so that means I have to go back to the drawing board again to think about the first one. Okay, so I'm defining what n is. I'm still saying that n is 1. We just didn't define, we didn't do the second part correctly. I'm still saying that n is worth 1 because of the square, not the number, the square here. So n, it's area, so we're multiplying. So times, how do I represent when there's 2 of them here like this then? If n is this, okay, well I see this then. Here's n. There's n. How do I represent the rest of it? We already did 2n. I'm going to say that it's n plus 1 more. I'm going to try that. How about n plus 1? Okay, and I've defined n as just being this side of the square right here. That means that this would also have to be n. And there is 1 more that I'm adding to it to get the whole side here. So now figure 1 would be 1 times 1 plus 1. 1 times 2 is 2. That works. How about over here? For figure 2, that's 2 times 2 plus 1. 2 times 3 is... See, it's all how you define it in the beginning. 4 for what? All right, so that's one way. I have to show you the different ways to be able to go about it. If I don't show you the different ways to think about it, you're never going to try thinking about it that way. All right, so there's a pattern that's going on here, a very clear pattern. I can see that these are going up by 2. And I can see that these are going up by 2. So these are odds. These are odd numbers, 1, 3, 5. How can I write an algebraic expression for odd integers? Consecutive odds. We had this on the summer homework. How could I write an expression that would show consecutive odds? Because if I can write it for consecutive odds, then I can go to consecutive odds to infinity. So how do I write an expression to show consecutive odds? That would be the top part of the area times the next part of the area, which is even integers. So how do I represent odd numbers? What's an expression that's going to help me to represent odd numbers? I have x. Is that going to make it even or odd? Well, how do you know? Plug in a number. What do you get? Plug in 1. Is that even or odd? If I plug in 2, what is that? So that just makes it even and odd, right? Just x. So what can I do to x to make it even? Let's start with that one. That's an easier one. How can I make this an even expression? Okay. So 2x. If I plug in any number here, is it still going to be even? Yes, because you're doubling it. So that takes care of this side of the area for the area. Yay! So if that makes it even, then I can add 1 to it, and it would make my even number odd. So I had, well, we don't know if it's going to work for the whole thing, but we are sure trying, right? So 2x plus 1 is the area of the top part going in odds. And so odd times the even, if I multiply this by 2x. So here's my odd top. Here's my even sides. There's area, base times height. Let's try that with the figure numbers now. Ugh. Not looking good. Oh, come on. Really, it did. I thought so too. And so, okay. Sometimes an issue that you have is whether you start with figure 0 or you start with figure 1. That sometimes can, let's just do some number crunching and see if we're getting anywhere close. Let's say that we do figure 1. So figure 1, figure 2. Just want to see if we can actually get any numbers to work. So if I use a 1, then what do we get? We get 2 plus 1 is 3 times 2 is 6. And then if I do 2, what do we get? 4 plus 1 is 5 times 4 is 20. And we don't have anything like that for area numbers, do we? Oh, darn it. That was looking pretty good to think that way. Well, it's not the only way to write odd integers either. Oops, somebody said something. Does somebody have an idea? Oh, I was just thinking that myself.
Who said it?
Let's see. Go to the chat. Jonah. Jonah says, how about minus 1? Now, if 2x makes it even, you can add 1 or subtract 1. It will still give you the odd on both sides, right?
Plus or minus 1.
So let's try minus 1.
Plus or minus.
That's still odd. 2x makes it even, and if I subtract 1 from that even number, it's still odd. Okay, so here we go. Let's try that number crunching again and see what happens. So figure 1 would be 2 minus 1, and then times 2 is still 2. And then if we try figure 2, we get 2 times 2 is 4, minus 1 is 3, times 4 is 12.
Yep.
Ching, 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 ching. Now, okay, for 3, we get 3 times 2 is 6, minus 1 is 5. And then we said 3 times 2 is 6. Wait, oh yeah, 5 times 6. Yay! I can't lead you straight to an answer. We have to have trial and error so that you can see that even though I said n the first time times 2n or n times n plus 1, just because it doesn't work for this one doesn't mean that that technique's not going to work for other ones. I actually, the next thing I was thinking was, didn't I just say there are different ways to represent odd numbers, right? I was getting there. Great job, Jonah. Thank you for that. Yay! Let's do 2 snaps and a clap for Jonah. Ready? All right. Here we go. S pattern task. Again, the same thing. You want to be looking for some patterns here. So start putting some things on your paper that you're looking for a pattern. This one's not too bad once you think about the one that we just did.
What do you mean?
I'll give you 5 minutes to start thinking about it. Well, notice that I wrote a formula myself, and then I could test my theory to see if that formula was true. Did you come up with one, Leah? I want you to think about area on this one as well. That's my hint. Not the final answer for area. Not like we did with all of the previous ones in linear. We'd add up the whole figure and we look at the pattern between how much was in the figure. Think about area. It's a quadratic. It's x squared. How do you get x squared? X times x. So you have to be thinking more about area instead of thinking linear. And it's not always easy to start on the first one. My other hint would be sometimes it's hard to start from the very first one. If you start from the second or third, then you start to see a pattern. what you can do for me on this section where we're way outside of your thinking, except for the regressions. You guys having any problems with the regressions? Those are pretty straight up, aren't they? When it comes to pictures and it comes to being good at transformations, what I need from you is to put your best foot forward. I need you to show me something so that I can give you some good credit for it. Am I expecting perfection at this point right now in your life? No, but I need to help you start moving in that direction. Okay? Because you will see transformations. You won't see pictures again. I'm the only one that does that. It's just something that I really like a lot. I think it adds to my math. I think it adds to my logic and thinking about math. So you're not going to probably ever see that again. I saw it in graduate school. They want us teaching you this way. And I said, yes, I do too. All right, so excellent job on that one. That was just wonderful. Trial and error. We had to try, what, 4 times to get to that.